Thanks very much.
You heard me say I'll get up in a few minutes left. You heard me say I'll get up in about 2-3 minutes left.
Forward and reverse. There is a severe damage due to acidic pollutants such as sulfur dioxide and nitrogen oxide. It is well known that activated carbons are good adsorbent for sulfur dioxide, but they are less effective for nitrogen NO adsorption. But they are less effective for NO adsorption. Although they have much larger adsorption capacity than silica gels or zeolite. So the good adsorbent for NO is desired. In earlier conference at Clarkson University last year, we reported the NO adsorption activity of activated carbon fibers is enhanced by treating it in ion salt solutions. In this symposium, I'd like to present a paper on micropore filling of NO in alpha FeOH, highly dispersed activated carbon fibers. May I have the first slide, please? The boiling temperature of nitrogen dioxide, and sulfur dioxide are near room temperature, so they are condensable on solids by physical adsorption or micropore filling around room temperature. But the boiling temperature of nitrogen monoxide is so low that we can't fix NO on solids by physical adsorption around room temperature. In such a case, we must use chemisorptive action. Alpha FeOH has very high chemisorptive activity for NO. We prepared alpha FeOH dispersed activated carbon fibers. They can fill NO at 30 degrees by 20 to 70% of the micropore volume. I'd like to explain the details in later slides. We use cellulose and pan-based HEF. We use the abbreviation cell and pan. We dispersed alpha FeOH on the HEF by treating it under the synthetic condition of alpha FeOH. That is, hydrolysis of ferric sulfate solution at 30 degrees and pH 30. We call this alpha HEF, and the alpha treated HEF will oxidize with nitric acid, alpha OX HEF. The surface concentration of FeOH was determined from the amount of ion deposited and the specific surface area. There is 0.2 to 0.7 FeOH unit per 100 square angstrom. The X-ray diffraction patterns of these samples have no peak, so we identify the substance by use of XPS. This table shows binding energies obtained by XPS. The binding energies of these samples are almost identical to those of alpha FeOH. So we consider Substance on the HCF must be fine alpha FeOH. We regard these samples as alpha FeOH highly dispersed activated carbon fibers. We determined the nitrogen adsorption isotherms. The isotherm is of type 1. We got T-plot. This slide shows micropore size distribution from T-plot by the method of Michael et al. The micropores are very uniform and their sizes are less than 10 angstrom. This slide shows DL plot for the nitrogen adsorption on cell samples. The ordinate is the logarithm of amount of adsorption. The abscissa is the square of logarithm PO by P. We can see a good linear relationship, and we determine the micropore volume and the characteristic adsorption energy from this plot. This table summarizes adsorption parameters determined from nitrogen adsorption. Each column shows surface area, pore volume, and pore diameter. Specific surface areas from BET and T plots agree with each other, and pore volume from T and DL plots will coincide. The pore diameter of these samples, determined by micropore analysis, are 7 to 9 angstrom. Now, I'd like to speak on NO adsorption. We measured NO adsorption isotherms by a conventional gravimetric method. This slide shows adsorption isotherms of NO on cell samples at 30 degrees. The amount of NO adsorption is expressed in terms of milligram per gram. Alpha-OX cell have the greatest NO adsorption capacity of these samples. Also, this slide shows adsorption isotherms of NO on cell samples. This time, the amount of NO adsorption is expressed in terms of microgram per square meter. The highest NO adsorption activity of alpha-OX cell is more clearly shown. This slide shows adsorption isotherms of NO on pan samples at 30 degrees. Also, alpha-OX pan had the greatest NO adsorption activity of these samples. This slide shows changes in the NO adsorption on alpha-OX HCF on introducing 4 kilopascal NO. The NO adsorption rate of alpha-OX cell is independent of the temperature. On the other hand, the absorption rate of alpha-OX pan at 15 degrees is larger than that at 30 degrees. This slide shows adsorption isotherms of NO on alpha-OX HCF at 15 and 30 degrees. The amount of NO adsorption of alpha-OX cell at 15 degrees is slightly larger than that at 30 degrees, while the amount of adsorption of alpha-OX pan at 15 degrees is much larger than that at 30 degrees. As lowering temperature promotes NO adsorption, so I'm sure that the NO is adsorbed by a kind of micropore filling mechanism. And we can see the chemisorptive action and the temperature dependence of alpha OX cell. Here, I'd like to compare the amount of NO filled in the micropores at 30 degrees with the amount of nitrogen filled at minus 160 degrees. This is the ratio of these values in terms of the number of molecules. Alpha OX cell is 50% and alpha OX span is 65%. Those micropores can be anomalously filled with NO by over 1/2 of the micropore volume at even 30 degrees. So we apply the DLR plot to the anomalous micropore filling of NO. We postulated the saturated vapor pressure of NO in the micropores at 30 degrees is equal to that of bulk liquid at minus 152 degrees boiling temperature. Thus, we can obtain the pseudo DR plot as shown in this slide. We can see a good linear relationship and we determine the pore volume for NO and the characteristic adsorption energy for NO. This is the saturated amount of adsorption for NO determined from Langmuir plot, Langmuir B values. And this is pore volume from the pseudo-DR plot. These two values agree with each other. And by use of the heat of vaporization of NO at boiling temperature and the characteristic adsorption energy for NO obtained by pseudo plot, we obtain the isosteric heat of NO adsorption. These values are almost equal to those of nitrogen adsorption. So we consider the state of NO in micropores similar to that of nitrogen adsorption, nitrogen. This slide shows adsorption isotherms for nitrogen on alpha OX cell before and after adsorption of NO at 30 degrees. The upper curve shows the adsorption isotherms without pre-adsorbed NO. On pre-adsorbing NO by this amount, the amount of nitrogen decreased, and this lower curve shows the adsorption isotherms of nitrogen after pre-adsorption of NO. The position of this isotherm is lower than expected from the amount of NO adsorption. There is a gap. This gap shows that almost all NO molecules are adsorbed near the entrance of the micropores. We examined the TPD spectra by use of mass filter in order to identify the adsorbed species. This slide shows TPD spectra of alpha cell with adsorbed NO. Evolved gases are NO, carbon dioxide, and nitrogen. There is a main NO peak around 150 degrees. We could not detect nitrogen dioxide, NO2, so we considered the adsorbed species is not NO2 but NO. As for carbon dioxide and nitrogen, they are produced due to the reaction of carbon with NO in the course of heating. We'd like to propose this model of the anomalous micropore filling of NO. The pore diameter of about 9 angstrom, being 3 times larger than the shorter axis of NO molecule. Almost all NO molecules are adsorbed near the entrance of the micropores. Alpha FeOH on the surface can catch NO molecules from gas phase and move into the pores to form the dimer of NO molecules. These adsorbed NO molecules hinder dissolution of NO from the micropores. Thus, alpha FeOH on the HCF assists micropore filling of NO to fix NO molecules from the gas phase and lock NO molecules preserved in these pores. So we think the alpha FeOH disperse activated carbon fibers shows chemisorption temporarily assisted micropore filling. And finally, I'd like to express my thanks to Professor Inoue for his discussion and to Dr. Soma for his measuring XPS data. Thank you very much.
Thank you. I certainly think we enjoy your English.
Yeah.
Good.
Yeah. Thank you.
Does anybody have any comments?
Excuse me. Slowly, please. Sorry.
Adsorption of NO on your carbon after just nitric acid oxidation without adding aluminum, putting a iron?
Just we determine the pure NO only. Do you ask another question?
If you treat the activated carbon with nitric acid, you oxidize the carbon. Did you look at the adsorption of NO on just the oxidized carbon?
Yeah. Just a moment. Slide, please. Sorry, I didn't the slide. So, the activated carbons fully oxidized nitric acid shows the lower activity for NO.
The slide is taken out of it. Any other comment or question? I think you have a comment.
In one of the slides, you have nitrogen adsorption before and after NO adsorption. Do you find it, or do you have an explanation of why nitrogen adsorption after NO adsorption was type 1 left? Does that mean there was still micropores?
Yeah,
Do you know
we
what-
think so.
There are still micropores open even after NO adsorption.
Yeah, probably the please light off, please. Probably NO molecules are adsorbed near here, but slightly a fall is exist. So we can obtain the type of one.
It's in, in one of these slides, you have nitrogen absorption before and after NO absorption. Do you find it, or do you have an explanation of why nitrogen absorption after NO absorption was type 1 flat? Does that mean there is still micropores?
Yeah, we think so.
There are still micropores open even after NO absorption.
Yeah, probably the please light off, please. Probably NO molecules are adsorbed near here, but slightly a fall is exist. So we can obtain the type of one nitrogen after introduced here, and probably there is no NO molecules here. So in such a case, nitrogen adsorbed around here, but probably after nitrogen pushes NO, probably, but I don't have the definite idea. Sorry.
I think, can I respond now? I think you've given a very interesting explanation, but I think that you need more evidence to support it, because I think that it is still open to question as to whether the nitric oxide adsorption itself is not taking place by chemisorption. I'm inclined to doubt your explanation. I'm inclined to question whether, in fact, you do obtain the promoted micropore filling in the way that you described. I think not. I think I offer a different explanation. That's my feeling. The second point is, I think that you have to be cautious in using the T-plot and the MP method in the way that you've done. So I would, and that doesn't take away from the results. You obtain some very interesting results, but I think you have to be careful in your interpretation.
Thank you very much. Thank you very much. Thank you.